version 2? Let's have a look at it now. Did you get my feedback, Matt?
Yes.
Oh.
I don't understand.
Good. That's always good feedback when the student doesn't understand. You don't understand all of it or some of it?
I don't understand what it means by the stuff or.
Yeah. So in your planning section, in your plan
for the column. Your tables need numbering. It would be nice if you had a few more subsections.
Yeah. So in your planning section, you didn't really have it divided as in like experiment 1, experiment 2, experiment 3. So that's not a big deal. Your tables need to have like little numbers on them, like table 1, table 2. The same goes for your graphs as well.
And also, should be in 3 or 4 columns.
Yeah, so like you had your item list, which is fine, but it would look a little bit nicer if it was maybe in 3 columns, so it doesn't take up so much space. Do you know what I mean? It's just more efficient use of paper. So, yeah, that's all. It's mostly style. Nothing major. Yeah. Okay. Have you got sorry, have you got version 2 open? Yeah, you have it open?
Yeah.
Okay. And hit us with A1, so.
State the difference between a scalar and a vector.
Ah, easy peasy. What's the difference?
Scalar has only magnitude but no direction.
Yeah. Scalar has only magnitude, but a vector has both magnitude and direction. Right, how many marks is that, Handek?
4.
No. Right, what's next?
This is B.
Okay.
The ship is pointing due north.
Okay.
And has a speed relative to water of 20 meters per second.
20 meters per second?
Yeah.
Okay.
The water itself is moving from west to east at 4 meters per second due to the tide.
So like this? Okay.
Sketch a vector addition diagram to show the resulting velocity of the ship.
Right, so the ship will head this way. Does it ask you to, it probably wants the calculation of
Yeah, this is B1 to B2.
I see, that's B1. And then B2 is to calculate the magnitude, is it?
The resultant velocity and direction.
Yeah. So that's root 416. What's that? Root 416. 20.4. And then the direction would be tan inverse 20 over 4. What's that?
Is it 4?
If I'm getting this angle, it'd be 20 over 4. And if it was that angle, it'd be 4 over 20. So what's that? So
Because it's relative to north, so isn't it?
no, you can give whichever angle you like. What is it?
78.7.
So my answer, Andek will be east 78.7 north.
Because mine is 20.
That's fine. So yours is north 20 something east.
Yeah.
Yeah, it's fine. Easy peasy, lemon squeezy. Yeah. Are we on to A2?
Yeah.
Okay. Siva will give us A2. We'll take turns. What's A2?
When a nail is driven into a piece of wood, a force must be applied to the nail by a hammer. The average force applied is 1,100 Newton, and during one strike, the nail moves through a distance of 1.5 centimeters in the direction of the force applied by the hammer. A. State
interesting. That's not really related to this topic, but okay. I think we know the story. You did say conservation of energy, didn't you? Not. Yeah. Okay. Okay. So conservation of energy states. We know the. What is it? Yeah. Do I even need to write it down? No. Okay. Energy can't be created nor destroyed, but transforms from one form to another. What's the next part? B, is it?
We determine the work done by the hammer during one strike.
Well that's just force by distance, which is 1100 times 0.015. And what do we get there? 16.5 joules. Is it? Yeah, okay, and C?
C, an observer comments that once the objects are at rest, the kinetic energy of the hammer has been lost in the process. Give a correct description of what has actually happened to the initial kinetic energy of the hammer by the end of the process.
Yeah, that's actually, that's not super obvious. So the conservation of energy, now I understand why they put that in. The conservation of energy states that you can't lose energy. So the question is, the hammer here had kinetic energy, then it hits the nail. Obviously the hammer stops when it hits the nail, and then the nail goes into the board, and then it stops. So the question is, what happened to the kinetic energy? What energy did it become? Yeah, so the kinetic energy became many other types of energy in the process. So you're right, and it became, number one, sound. What else, Siba? Heat. The nail is actually a little bit warmer. Yeah. And there's one more form of energy, and I wonder if anyone can spot it. Yeah, very good. Potential energy. Because, think about it. The nail is trapped now. So if you wanted to pull that nail out, you would need some energy to free it. So because it's in the wall now. Yeah. What's so funny?
It's mostly describe or explain.
Is the exam? Yeah. Is that the end of that question?
Yeah.
Okay. Matt, you can give us number 3 now.
The graph shows the temperature of water against the thermal energy transfer.
Is there any times, or is it just a shape and you have to, is it one of these name what happens at each, yeah, I see, so it goes up, across, less across. Great, okay.
Copy the graph into your answer with a table and name the changes of state shown.
This is energy, isn't it?
Yeah.
And this is temperature. And I assume this is 0. Did I draw that graph right?
Mm-hmm.
It isn't flat at the start. So, I mean, it goes straight up at the beginning.
It didn't say it's 0.
Just like that.
Oh, they put nothing on the axes. Right, so it's possible that this is could be in Kelvin. So it could be that here, probably here is what they mean is 0 Celsius. Or maybe if it's in Kelvin, that's 273. Yeah, you know what? Maybe it's Kelvin. Not sure. But anyways, we'll go with that. Okay. So what they want you to name the change in states. Is
Label
it?
and name
Yeah.
the changes of state shown.
All right. So that first one there is obviously melting, and then this one here, boiling or vaporization. Okay, next, Matt.
Einstein used the observations of Brownian motion to confirm his atomic theory. Explain how Brownian motion provides evidence for the movement of molecules.
What was the first half we had to do? Describe Brownian motion?
It's
Okay,
explain.
explain. So Brownian motion, is when you have, imagine we're looking under a microscope. Let's say we have something here, some small particle. Usually the example they use is a piece of pollen or something like that. You know what pollen is? It's what comes off the flowers. And if you look under a microscope, it actually moves like this. It kind of moves around randomly. Now the reason it's doing that is because what you can't see are these small little particles. They hit into it and they cause it to move. So that's Brownian motion. So Brownian motion, we can say it's a type of random motion due to random collisions. So if you want to picture it, like here it is here, if you look, a particle would hit it, and then another one would hit it, and then another one would hit it, and it just looks like it's moving around no direction, randomly. This is a Brownian motion.
What's the last word?
Collisions. This type of motion is given a name in maths. It's called a random walk. Is the technical name for it in maths. A motion that has no direction. It's just completely random. Now the second half was explain why this gives evidence for the kinetic particle.
Movement of molecules.
Yeah. So obviously the reason for the random walk can only be explained by the collision of small particles. I'll try and explain, you know, if you were looking at something in water, if I can draw here, you know, you would see it move, maybe it goes up, or maybe it goes down, or maybe it goes like this, okay, because water is a liquid. Now if you zoom in to something really small inside the liquid, instead of moving like this, it'll move like this. Now that's different motion. So it must mean at the very small level, you don't have a liquid anymore. Instead, you just have water molecules, particles. So the motion changes when you look small enough, meaning at the basic level, it's not really a liquid, but actually everything is just particles. This is kind of the idea. Okay, is there more to the question, or is that it? Okay. Chow, what's A for?
Electric currents can follow through the electrode of a battery, and also through the copper wires attached to it.
What's the question?
A1?
Yeah.
Give one similarity and one difference between the flow of electricity in each of those cases.
Okay, so the first one is in a battery, did you say?
Yeah.
Okay, so that might be something like this. And the second one is in a copper wire, is it?
A copper wire.
Right, and the question is, give something that's similar and something that's different, is it?
Yeah, between.
Okay, let's start off with similar. What's similar here? Well, yeah, they're both a conductor. So they're both conducting a current in one direction. I don't know, did they say that? If they don't say it, then I don't know.
They didn't say anything about the same value.
Yeah. But what's the difference? That's a similarity, but what's the difference? Well, there's an obvious big difference. Something.
Materialistic.
Yeah, but I mean, like, what's different in each situation?
One has the sun.
Yeah, so, like, how does that make the story different? Yeah, come on, give me sentences with verbs, please. Was there a verb in that sentence, or did you just say power out? You guys don't like giving me sentences. Give me a full sentence.
One has a power supply, one doesn't.
Yeah, but why is that important? Like, what difference does that make? You know?
One has a current and one
Yeah, well, no, but they both have a current. No? Oh, guys, okay. How about we could say the first one provides a current, whereas, where,
But this uses charge carriers.
yeah, current. Wait, for what? Similarity or difference?
Difference.
What's it say for a difference?
Sorry?
What's it say for the difference?
Charge carriers. Ions versus electrons.
Oh, yeah, okay, that's fine. Wait, maybe I misheard you. Is it just a battery?
Electric current can flow through the electrolyte of the battery.
Oh! Okay, electrolyte battery. Okay, sorry. So, the picture is more like this. You have your battery, and then you have a copper wire. Now, what's similar is the same. That they both conduct a current. So the difference they gave in the marking scheme, yeah, that's fine. There's other differences too. That's fine. In this one here, the current is moving because there's a movement of ions. Whereas in this one here, the current is moving because there's a movement of electrons. That's one difference. Also, this is providing a current, but maybe I'm not fully hearing the question. What is the difference in the current? Or what is the difference in...
If one similarity and one difference between the flow of electricity in each of these cases.
Between the flow.
Of electricity.
Okay. Right, so similar, same direction. Difference, ions versus electrons. Right, there you go. Okay, what's next?
What is he say? Net or bulk movement of charge over time.
For what? Similar?
What it is.
Say again?
Net or bulk movement of charge over time.
What movement of charge?
Bulk.
Bulk.
Oh, that's not an academic word. Net or bulk movement of charge. Oh yeah, so all they're saying is both of them carry a charge. It's a conductor, it's just saying it's a conductor. Yeah, the same direction of current in conductor.
Sounds so fancy.
It does, yeah. Right, anyways, what's the next part, Joe?
That's why the amount of charge which leaves or enters the positive terminal of the battery when a current of 3A flows to the battery for 50 seconds.
50 seconds?
Yeah.
150 coulombs. Okay, what's next?
85.
85, okay. Back to you, Andek.
Define electric field strength.
Electric field strength. Okay, so, do you want words or formula? Huh? Formula is E equals F over D, where that's the electric field strength. This is the force felt by the charge. Oh, sorry, I wrote D. Sorry. This should be, of course, Q. And Q is the charge held. So in other words, the electric field strength is the force per unit charge, with the units obviously being newtons per coulomb. Surely that must get me my, what is it, 1 mark?
Yeah.
I must have my 1 mark. What's next?
In the region around a point of charge for millicoulombs, is that millicoulomb?
Yeah.
There is an electric field. Determine the electric field strength at a distance of 20 centimeters from the point charge.
20 centimeters. Okay, so this one, I'm not sure if this is in the formula book, it probably is, but it's the formula 1 over 4 pi epsilon 0 q over r squared. It is in the book.
Yes.
That's 8.99 times 10 to the 9 times 4 times 10 to the minus 3 over 0.2 squared, I hope. Man, I'm so ready for this test. I'm going to get an A star. I hope you guys are ready for it too.
Yeah, I got it.
Yeah?
8.99 times 10 to 8.
In total, 8.99 times 10 to the 8.
Yeah.
Yeah, newtons per coulomb. Next. Oh, how many marks was that? Okay, that's okay. What's next?
Sketch the electric field lines and its potentials
Sorry,
around
say again, sketch the electric.
electric field lines and the equal potentials around the point charge.
Our point charge, I think, was positive 4 millicoulombs.
Yeah.
Okay, so this is the field lines. I'm not going to do lots. Whoops.
Do we have to like draw 2 arrows in a line?
You know, if it was me being fussy about it, I would say yes, because you need to show that the field is getting weaker. Now, maybe whoever does the marking scheme just doesn't bother and just draws 1 arrow, okay? But the reason I'm drawing 2 is I'm trying to show that the field gets weaker as you move out. So at least 2 will do that. And I'll just write in my answer, in red is the field lines. And then we want the equipotential lines. Do you remember what they look like? They're circles, yeah, very good. And then these are the potentials. Okay, fine and dandy. How many marks was that one, Anda? 3 marks. Nice. Right. What's next? Or is that it for that one?
A6.
A6. Siba, A6.
A, give one similarity and one difference between the properties of infrared and ultraviolet electromagnetic radiation.
Okay, so we have infrared and ultraviolet. Right, let's focus on something that they both have the same. Well, they're both electromagnetic waves, so it means they both travel at the speed of light. That's an easy one. But now a difference. Yeah, wavelength now, or frequency. what I'll do is I'll say this one is frequency 1 and this one is frequency 2, and here, or I'll write actually frequency infra, that's less than frequency ultraviolet. Same here. I'll just write it the other way around. Frequency of ultraviolet is more than frequency of infra. And it's not infra, sorry, it's infra, isn't it? There's an or?
Yeah.
Yeah. Not that you guys care. Well, maybe you care, I don't know. Do you care? Right. How many marks for that one, Siva?
2.
2. Yeah, so it's going to be 1 mark for the V equals C and 1 mark for the frequencies.
B.
Mm.
Experiments show that electromagnetic waves can be polarized. Explain what this means.
Ah, so does anyone remember what polarizing means? To polarize a wave means what? To, you know, Siva? To confine its vibration to one plane. So I'll just try and draw a picture. You might remember this picture. So what happens is you have a little slit here and your wave is coming in, but it's vibrating in many different directions. Yeah. So like it's vibrating in horizontally and maybe it's vibrating in vertically. But when it passes through this slit, it's only vibrating vertically. So you've confined it to one plane. That's what it means. How many marks for that one, Siva? 1. Okay. What's next?
A7.
Oh, go ahead, Matt.
The 3 main types of ionizing radiation are alpha, beta, minus.
Oh, I was hoping you were going to say what are the 3 main types. Yeah, they're alpha, beta, and gamma. Go on, yeah.
A1, which of these is the most highly ionizing?
Yeah, okay. So, which is the most highly ionizing between the 3 of them? No, I think it's gamma. I think
They ask
so.
highly penetrating science, you can do that one.
Well, the highly penetrating one is definitely gamma.
Yeah.
Oh, sorry, yeah, that's right. There's an opposite relation here. Let's do the other question first. What's the next part?
Which of these is the most highly penetrating?
Right, the most penetrating is definitely gamma, for sure. Because remember we said it needs a concrete of a meter of concrete. Oh yeah, so then that means, sorry, I got it backwards. So the one with the most energy is alpha. And I said that's a good thing. Alpha has the most energy, which means it does the most damage, but it's the one that's most easily blocked. Remember we said you could actually block alpha with some clothes. So yeah, they have the opposite relationship here. The one with the most energy has the least penetrating power, and the one with the most vice versa. What's the next part? Or C?
Define D.
D?
That's A1, A2.
Ah,
So now it's D.
okay.
Define the term half-life for radioactive isotope.
Okay, so do you remember half-life? It's the, that's it, the time taken for, go ahead, what are you going to say, Andak? Yeah, half of the sample to decay away. Or maybe be a bit more technical, half the sample to become non-radioactive. Okay, next. Really? How many marks for that?
3.
For me?
I mean,
Altogether.
altogether.
Okay. A8, Jeff?
A low pressure gas can produce an emission line spectrum. Explain how the extents of this spectrum provides evidence about the structure of the gas atoms.
Good, okay. And you said it's emission with an E, is it? Emission?
Yeah, emission.
Yeah, okay.
Emission line spectrum.
Good. So I'll remind you of what's happening here. If you heat this gas up, it will obviously glow. There'll be some light that comes off of it. Then if you put that light through a prism, then it splits. And here you get your colours. You know, red, orange, yellow, green, blue, indigo, violet. However, some of the colours will be missing. So you might look at it and you might see, here's the red. Here is the red. Oh goodness, sorry, that's black. Here's the red, and then it turns into green. Okay, but maybe a little bit of the red might be missing here. Maybe a little bit of the green's missing here. Maybe a little bit of red's missing here. You don't get a full rainbow. Some little pieces are missing. Okay, and what's the reason for this? Well, what's happening is inside the gas, you have your nucleus, and you have your different energy levels. Okay. Now, I'll try my best. I'm going to zoom in. So there is my proton. Let's say it's hydrogen. There's my energy. There's my electron. First orbit. There it is. Second orbit. Okay. So what might happen is, what happens when an electron moves from here down to here? Oh, I mean to say, what happens to the energy? Does it get more energy or less energy?
It's less energy.
It's less energy. It loses energy. Yeah? And then what about if it moves from here up to here? It gets energy. It has a higher energy level. Okay? Huh? Oh. Okay, let's see. So like for example, I'll just put in some numbers. So we could say, for example, see at the first orbit, maybe it's -1 electron volt, and then, like -2 electron volts, and then on the outer orbit, maybe it's -1 electron volt, and then when it's free, it's 0 electron volts. So if it goes from a -2 to a -1, then it's gaining energy. Yeah? And if it goes from -1 to -2, it lost energy. Now remember we said energy can't be created or destroyed, right? So what happens to that missing energy? You know, if this jumps down from here to here, 1 electron volt is missing. Where did it go? Yeah. So what happens is it releases a photon. That's why the gas glows. It gets really hot. The electrons jump levels and they release photons. The photons will have different frequencies because the energy levels are different.
The cancel?
Yeah. The energy of the photon equals the energy here. Is that what you mean? Yeah. So anyways, what's happening is, the reason some of these energy levels are missing is because you're not able to get a photon with that energy level. Because remember, you can only jump certain levels, which means you can have only certain energies, which means you can have only certain frequencies, which means you're going to miss some frequencies. So what's happening is the photon's energy is equal to HF. And HF will equal the change in the energy levels. Therefore, it is not possible to have every frequency, because you can't have every possible change in energy. Like, for example, could I make half an electron volt? No. I can go from 2 to 1. Maybe I could go from 3 to 2. Maybe I could go from 6 to 2. But maybe I can't go from 1 to a half. So that's why some of them are missing. Yeah. Okay. So I think that answers that. How many marks is that?
3.
Yeah, okay, 3. So they need a bit of a work of art, perhaps. What's next?
We just point out that it releases a photon.
Yeah, but you need to say why you don't have every frequency and what's happening. The whole story. What's next?
No.
Oh, wait, 9. Okay, go ahead. And yeah.
We have to draw everything.
Pictures are good. You don't have to draw the pictures, but
So the electron is jump from 1 electron volt to 2 electron volt.
oh, in my made-up example, it went from -1 to -2. That means the photon that was released has an energy of 1 electron volt. Yeah? Go ahead, Ante.
A suspended spring has an unstretched length of 0.23 meters.
So again, the suspended spring has a length of
23.
Okay.
Unstretched. That's it.
Yeah, okay.
When a mass of 0.35 kilograms is attached to the lower end, it extends to a total length of 0.34 meters.
0.35 kilograms?
34. Yeah.
And the extension,
0.34 meters.
okay, is total.
New length.
So I need to subtract,
So the first one is determine the strain of the spring once the mass is attached. So
yeah, is that 0.11
11.
meters is the extension. Okay, sorry, what's the first part?
Determine the strain of the spring once the mass is attached.
That's the K. So you can say F equals Kx going up, and that should equal the weight, which is equal to mg. So K will equal mg over x, which will be 0.35 times 9.81 over 0.23. What's that? Problem with that?
Where's the question here?
Isn't that what it says? What's the K?
Determine the strain.
The strain on the spring.
Determine the what? Strength
Strain.
of the spring.
Yeah.
That's the K. I would hope so.
Because I follow the equation of strain equals to extension over length. Because we define extension strain.
Strain!
Yeah.
I thought you guys were saying strength. Okay.
Okay.
Now I understand why you looked confused at me. Strain. S-T-R-A-I-N. Okay. That is for extension over natural length, which is 0.11 over 0.23. What's that?
0.478.
Okay, great. What's the next part?
Determine the spring constant K.
That's what I just did. You could have told me I could have just numbered them differently. Right, so the K is, what did I just say? I said Kx, so the x is down, it was mg over x. Wasn't that what we said? So that's 0.35 times 9.81 over 0.23.
Over 0.
Oh, sorry, over 0.11. Sorry. 31.2. Okay, next.
When the mass is removed, the spring returns to its original length. What is this behavior known as?
What is the what?
What is this behavior known as?
Read that again
When-
carefully.
When the mass is removed, the spring returns to its original length. So what is this behavior called?
What is this behavior called? What is this behavior called? Well, I know what the motion is called. It's simple harmonic motion, but the behavior is it's restoring back to its original length.
Shouldn't that be elasticity?
It's elastic, yeah, but I'm just confused by the word behavior. Behavior?
Yeah, maybe
Behavior? Restoration behavior? I don't know. What's the answer in the marking scheme?
Elastic.
Just elastic. But is elastic really a behavior? What is he saying? I don't know. I'm not satisfied with that. Was it one mark only?
Yeah.
Yeah. I guess I wouldn't get 100% in that exam, because if I was a student doing that exam, I probably would have said restoring behavior or simple harmonic motion. I don't think I necessarily would have thought of saying elastic. Even though it is elastic, it doesn't quite match in my head the word behavior, you know. Right, what's the next one?
8, 10.
So anyways, what I'm trying to say is it's okay if you don't get 100. It's okay. I'm not expecting that. 810. Go ahead, Siba.
A ray of light is incident on a glass block of refractive index 1.43 at an angle of incidence of 20 degrees to the normal. A. Determine the speed of light in the glass block.
Okay, so do you remember the formula? It's N equals C over V, isn't it? Isn't that it? So the V that they want is C over N, which is 3 times 10 to the 8 over 1.43. So what do you get for that?
2.19 times 10 to
Thank you. Right, what's next? See that?
B. Determine the angle of refraction of the ray as it enters the block.
Okay, so that's sine I over sine or equals N2 over N1. So that's sine 20 over sine or equals 1.43 over 1. I assume it's coming from air or something like that. So that means the or would be sine inverse sine 20 over 1.43. Thank you. Is there C?
13.8.
Is there C?
Yeah. Determine the critical angle for a ray of light traveling inside the block as it reaches the glass
Okay.
air around it.
There you go. So whatever that works out to be. Right. Are you next, Matt? What number are we on?
B1.
Oh, great. Okay. So what's B1 about? Is it a mechanics? What's it look like? Mechanics?
Yes.
Okay, go for it, Matt. B1.
What?
Wait, what is it, like B1A part 1 or what's the number? Okay.
What is meant by a vector quantity?
Oh, didn't we do that in section A? Okay. A vector has magnitude and direction. Okay. Number 2.
A2. Which of the following are vectors?
Oh, good. Right. So let's write them down and then we can talk about it.
Speed,
Okay. Speed,
force,
force,
acceleration,
acceleration,
velocity.
velocity. Anything else? Okay. So speed, vector or not? No. Force? Yes. Acceleration? Velocity? Yeah. They're all vectors except for speed. Okay. Next.
B. A piece of string is used.
B1.
B.
Okay.
A piece of string is used in conjunction with a peg to help.
In conjunction with a what?
With a peg.
A peg. Okay.
To help hold up a tent as shown below.
So let me guess, is it going to be, there's this thing here, and there's a wire here? No. Oh, much more interesting. Much more exciting. Okay, go for it, Matt. What's that?
Peg is
Huh?
the
Peg is the thing you hammer into the ground, yeah. It's like a nail, really. It's usually, pegs are usually just made of wood.
Yeah.
Yeah.
No, it's what's the
The tension
Yeah.
in the string T is 100 Newton.
100 newtons.
B1. Determine the horizontal force on a peg due to the string.
The horizontal, okay, so there's a force this way and this way. So we just want 100 cos 25, right? The horizontal one. So what's that? See, but do you have it there? What is it?
19.6.
19? 90.6 newtons. Right, next.
A2. Determine the vertical force on a peg due to the string.
Really?
Yes.
100 sine 25? Okay.
42.3.
Right, next. Part 3.
A3. B3. The angle the string makes to the horizontal is reduced whilst the tension remains constant.
Don't tell me they're just asking you to...
State the effect on these
Ah,
on the vertical and horizontal.
Classic question from him. Classic. So he wants to know, if you reduce the angle, what happens to each component. Right, so what would happen to the horizontal if you reduce the angle? So you need to think about, if you change it from cos 25 to say cos 20, it increases. And the other one, yeah, so the horizontal, we said increase, and the vertical decreases. Okay.
C.
That was it for B. Okay. C.
A beam is attached to two narrow supports, X and Y.
Oh, so it's like this, and it's a hanging?
It's
It's... Oh, okay. It's an interesting picture. We have a beam. We have a support here, a support here. This distance is 7 meters, and this is 1.5 meters. And you have a weight here of 2.5 times 10 to the 4 down here. Well, maybe it's not so bad. So the first one is state the principle of moments. So what's the principle of moments? Yeah, yeah, go ahead, Matt. I think that's fine too. Did you have something different?
force times perpendicular distance from line of action.
Oh no, that would be the definition. I think that would be the definition of a moment. But the question was, what is the principle of moments? So yeah, you said it there. It's that the total clockwise moments at a point in equilibrium equals the total anti-clockwise. Okay, what's next? Matt?
C2. Determine the magnitude and direction of the vertical force on the beam at support X.
At X here. Right, so look, there's two forces here. An or, an S. Oh, Matt, does the beam have a weight, a mass? It doesn't? It's a massless beam. Okay. For now it's massless. Okay, fine. So we want, is it the or? Is it the support at X, they said? Right. Right.
Determine the magnitude and direction.
But we must know the mass of the beam.
You know the distance to where.
Okay, well, oh, fine. You said the beam is massless, or
Assume the weight of the beam is 90
good, right? So that means there's no weight, massless. It's a light beam. Okay, so fine. That makes our lives easier. So where will we take the turning point? We want the ore. So I'll take the turning point here. Okay. So that's 7 times ore should equal 1.5 times 2.5 times 10 to the 4. So the ore is that over 7 and the direction is upwards. So what is that there, please?
5360.
So what do you need the mass of the beam for?
Well, in case there's another force. Yeah. I don't need it, I didn't want to miss it if there was one.
But yeah, like clockwise.
I took the turning point as the middle. Is okay? Right, what's next?
There's 2 ones.
C3. Determine the magnitude of the vertical support force on the beam Y.
So get the S now.
Yes.
Okay, that's fine. That's actually easy because you can just say ore plus S equals 2.5 times 10 to the 4.
So
Yeah?
the last question, the answer is downwards.
Well, I'm sorry, what did they say precisely was determine the
Magnitude and direction of the vertical force on the beam that supports
on the beam. On the beam or on the support?
on the beam at support X.
I think I might have to read it to fully process it. Thank you. Determine the magnitude and direction of the vertical force on the beam at support X. Stupid picture. It's not. Oh, I'm sorry. I thought it was standing on X, but it's like it's stuck into the wall, is it?
Yeah, this question is
Glued to the wall.
Oh, yeah, of course. Yeah, of course.
Is the picture like this?
No, it's like this. Yeah, I totally screwed that up. It's the beam is stuck into the wall. It's like pushed into the wall. Now that's important. I mean that makes much more sense. Sorry, I wasn't thinking about what was happening. So if we take this as the turning point, okay, this guy will want to make the beam turn this way. So the beam is trying to turn up here. So it must be that the wall is pushing down on it.
I think it's more. I was thinking.
Yeah. So that's why you're saying that this is wrong. Oh yeah. No. That's okay. Yeah, I was wrong, but I got the right answer. This is right now. Yeah. But it means this one is wrong because it's not or plus S. It's or. Yeah. Sorry. This should be like a minus or. It should be over with this guy on the other side. So I'll just put it over there. Oh, which is good because we know that one. Okay. So what's the S here? I should have looked at my picture more carefully.
3.04 times 10 to 4. So,
Are you sure?
30360.
30360 newtons, yeah? Okay, what's next now, Matt? D?
C4.
Okay.
For the following questions, assume the beam is uniform and now has a mass of 5,000.
Now it has a mass.
5
Okay.
times 10 to the power of 3
5 times 10 to the 3 kg. Okay.
Determine the distance from support Y to the center of mass of the beam.
Oh, first just work out.
Y is the ES.
Say, determine the distance.
Determine the distance from support Y to the center of the mass.
Oh, okay. So if the whole thing is 8.5, then the center of gravity should be here at 4.25, and the Y here is at 1.5. So they want this distance, is it? Yeah. So that's 4.25 minus 1.5. 2.75? Okay, 2.75 meters. Right, what's next?
C5. Determine the magnitude of the support force on the beam at Y.
Which is S.
Yes.
Okay. So, what I'm going to do, because I want the S, is I'm going to take this as the turning point. Can you see at the wall? Can you see that there? I'm taking this as the turning point, okay? So this one is clockwise. So clockwise 4.25 times 5 times 10 to the 3 times 9.81. The S is, how far away is the S? 7, but it's anti-clockwise, so minus 7 S, and then the last one is plus 8.5 times 2.5 times 10 to the 4. That should equal 0. Yeah? So look, this guy, I'll just take it over here. That's a 7S, and then divide by 7.
Sorry, the first 4.25 times.
Yeah, that's the distance from the end to the the center of gravity.
In the equation, 4.25 times 5 times 10 to the 3
Yeah.
times derivative.
Yeah.
That's the whole thing.
Yeah, for the first one.
Yeah.
Yeah. Okay, so what's the S there? Is okay, Joe? Okay. Is the next part, what's the or?
Yes.
Right, so we can just say from the picture, you can see that or plus the weight, what was the weight? 5 times 10 to the 3, wasn't it? Times 9.81. Plus 2.5 times 10 to the 4. That should equal S, which is 6.01 times 10 to the 4.
I really want to include 9.8.
Oh, if it's a force. So we need to make it a force. So the or is 6.01 times 10 to the 4 minus 5 times 10 to the 3 times 9.81 minus 2.5 times 10 to the 4.
1.4 times 10 to the power 4.
Is that the end of B1?
Yes.
Thank goodness. Okay. Now, we've got time? Yeah, we do. What's B2 about?
B2
Yeah,
part A1
yeah.
defined the Farad.
Farad, yeah.
Farad.
So, 1 farad, if you remember the formula, Q equals CV, isn't it? Sorry. C equals Q over V. So 1 farad is 1 coulomb held per 1 volt of potential difference. Okay, what's next, Chow?
A capacitor
Yeah.
is used to store the energy to light a flash bulb for a camera.
Hmm?
And the capacitor is charged to 6 watts and must store 100 millijoule. That's the capacitor of the required capacitor.
Okay. So calculate C.
Yeah, calculate C.
Okay. So we have the formula work equals a half CV squared. So you have 0.1 equals a half C times 36. So C would be, that's 0.1 over 18. So what's that?
5.56 times 10 to the power minus 3. So,
Farads. Yeah,
Is it always half CV squared
for the capacitor.
for the work?
For the capacitor, isn't it? Yeah, I think so. So it would shock me if it wasn't. Why are you thinking? Okay. Right, what's next? A part 3, is it?
B.
B, okay. B.
The capacitor then discharged through a bulb of a resistance 1.5 ohm. Ensure the resistance is constant. B1 that might
Yes, determine the
internal current through the pole.
the current.
Yeah.
Right. So, what could we use? We have VI or. We know or. We know V, don't we? Or do we?
yes. Yeah. 6.
Yeah. Yeah. We also actually know. Yeah. Okay. Something feels a bit wrong. I equals V over or. What's that? 6 over 1.5. Is the answer 4?
Yeah.
4? It is? I'm right. Okay. Next.
And that's the time taken for the voltage to fall from 6 watts to 2 watts.
Okay. 6 volts to 2 volts. So you have to use this formula. V equals V0 E minus T over tau. What do you say? We want to go from 2 to 2, is it?
6 volts
yeah.
to 2 volts.
2 equals 6 E minus T over... Now, who remembers how to get tau?
C.
Or C. The or is 1.5, and what's the C? What's the C? Oh, there it is. If you multiply those two numbers together, what did you get for tau?
8.34 times 10 to the power minus 3.
So that would be 0.00834. Right, so our job now is to solve this for t. You know how to do this. What do you do first?
Divided by 6.
And then? And then? Multiply the 0.00834. So you're going to have 2 over 6 first. Then you're going to log it. Then you're going to multiply by minus 0.00834. And that will give you the t. After you do this 100 times, you can do it in your head. You can, you know. It's the same process. Bring down the 6, log, and then bring up this guy. Okay, so what did you get? Well, what's the t here?
9.16 times 10 to the power minus
Okay, next, Sharon.
B3.
Tree.
B3. That's why the time constant of the discharge.
Really? Determine the time constant? But that's what we have to do to get that answer. The time constant is RC, which is 0.00834 seconds. So they must have some other way to do part 2 in the marking scheme. What? Yeah, but
There are no other ways.
There was no other way.
so they ask you to do something that needs the time constant, and then the next part asks you what the time constant is. Are you sure? Yeah, alright. That's weird.
They want to confuse us.
Yeah, I think so. Right, what's next then?
C1. And that might the charge stored by the capacitor when it is fully charged.
The Q. Okay, so Q equals CV. What did we say the C was earlier? 10 to the 3. And the V is 6, isn't it? Right, so what's this then? 0.0 coulombs. Right, next chart.
C2, if the charging process is carried out at a constant current of 5 mA, that might the time taken to charge the capacitor to 6 volts.
Okay, so that's fine. That's using the 6 volts.
6 volts. Back again.
No, I think. Yeah, no, that's just using the formula Q equals IT. T equals Q over I, which equals 0.0334 over 0.005. 6.68 seconds. Okay, next.
D.
D?
Yeah.
Okay.
In other applications, a capacitor are combined to give greater energy storage capacity. For capacitors of 2200 mF are connected in parallel.
Okay.
And are charged from a 10 volts power supply to a resistor.
Okay, good.
And one, determine the total capacitance.
Okay,
of
total
the
capacitance first, yeah. And you
capacitance.
said each one is 2,200.
2200.
So the total capacitance is 4 times 8,800 milli. Good. Right, what's next? Let me guess, what's the total energy? Is
Yeah,
it
total energy.
total energy. So that's a half
Stars.
C.
And when the arrangement is charged to 10 volts.
10 volts. So it's like this, isn't it? 440 joules?
Yeah.
Okay, next. Wait, let me guess.
Guess.
It's put in series.
Yeah.
Yes, in series. And they ask,
Yeah.
what's the energy now?
Yeah, what's the total, the new
Total
value
capacitance.
of the total capacity?
And then is the next question, what is the...
No.
Oh, they don't ask you to get the new energy. Fine. So it will be 1 over C is 1 over 2,200 plus 1 over 2,200 4 times. So 1 over C is 4 over 2,200. So C is, what's it, 550? If you flip it,
0.455.
550? 2000, Chow, what's 2,200 over 4? Is it-
0.555 farad.
Yeah?
So kind of received back the
Yeah.
current.
Sorry? 2200
00
2200
divide 4.
divide 4. That's
Is it
550.
Yeah.
220.
Isn't it 22? It's 22.
Because you said 220 divided by 4, isn't it? The other now, 4 divided by 220.
Oh yeah, but that's for 1 over C. So I flipped it.
Yes,
Yeah.
550.
I think
Yeah.
the math is so
Why, what did it say?
0.455.
Did they not flip? What's 4 over 2,200? It'd be funny if they didn't flip it.
4 over 2,200.
Yeah, what you get?
1 point.
Oh, okay. Totally different.
If you flip it, 550.
Yeah. So they said 450.
It's like a cross multiplication, so 4C equals to
Yeah, so they have a mistake.
the
How do you think they made the mistake? Did they just mistype it, or
Because they wrote the same numbers and the answer is wrong.
okay, so they wrote 2,204.
Yes, they wrote 2.2 over 4.
Yeah, okay. So they mistyped, or they did something silly. So whoever wrote the marking scheme also doesn't get 100%. Yeah. Right, what's, oh no, that's the end of that one, isn't it? What's A3 about? That was A2's finished, yeah? Or is there more?
yeah, that's it.
That's it. What's A3 about?
You mean
Oh, sorry, yeah, B3, sorry, yeah. Yeah, Andek, what's B3 about?
A transformer is to be used to step down the voltage supplied from 5 kilovolts.
Yeah.
The transformer consists of a primary coil of 2,100 turns and turns around the iron core and 100 turns on the secondary coil.
Yeah. What's the voltage, is it?
If the voltage across the primary coil is 5 kilovolts, determine the voltage across the
Is that A part 1?
Yeah.
So, you know, it's 5,000 over V2 equals 2100 over 100. That formula. V1 over V2 equals N1 over N2. Cancel, 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 cancel. V2 is going to be 5,000 over 21, which is, what is it? 238 volts. Okay, A part 2.
A power of 2 kilowatts is required from the secondary coil. Determine the current in the secondary coil.
Okay, so the I would be 2. Oh, that's power, isn't it? Sorry. You want the I, which is V over R. But we don't, yeah, we have to use the other formula, P equals IV. Yeah, sorry, so I is P over V. Yeah, so that's going to be 2,000 over 238. What do you get?
8.4.
8.4 amps. Okay, what's next now?
If the efficiency of the transformer is 95%, show that the power input required to the primary coil is approximately 2.1 kilowatts.
Okay. So you have the formula efficiency equals power in, which is what you want, over power out times 100. So power in is going to be 2,000. No, I've done something silly there. Oh, I have it upside down. Upside down. Power out over power in times 100. So power in is 2,000 over 0.95. Right, what's that? 2,100, is it?
I got 2.1 kilowatts.
2.11
kilowatts.
Okay. A part 4?
Determine the current in the primary coil.
Hey, right, so,
Same formula.
P equals IV, yeah. I equals P over V. Is it 5,000? Okay, what's that?
0.42.
Okay. A part 5?
It is suggested that the efficiency could be improved by constructing one of the coils from a low resistance material. State with reason which of the two coils should be chosen.
Ho ho! That's a juicy question. We've never seen that in class before. That's a very hard question.
It's 2 marks.
Yeah, so the question is, if you had to pick a primary or secondary coil to improve, which one would you pick? Now, I know that the higher the current, the more heat loss you could have. So I feel like you would want to improve the high current coil. And in this question here, the current with the higher coil is the secondary current.
Yeah.
Now, I'm prepared to be totally wrong here.
No,
But
it's correct.
okay. So the answer is the secondary current, the secondary coil, because it's the high current coil. Now, that's a very hard question. That's a very hard question. Okay, next.
The transformer is kept inside an aluminum
This
box.
is like part 6 now.
5. Oh no, sorry, 6, yes.
It's we're on 6, okay. The transformer is kept in an aluminium box.
Yeah.
Oh, is this going to be that the box gets hot?
When in operation, it is noticed that parts of the aluminum box became harm.
Yeah, okay, go on.
And suggest a reason for this heating effect and a way to reduce or eliminate it.
The transformer loses. No, what was the fancy word? Dissipates. The transformer. No, let's not. Yeah. The transformer lost heat to the surroundings of the box. And how could you keep the box cool? How could you help keep the box cool? So why does the box get hot? Because the transformer gets hot because it loses heat as a waste. What could you do to keep the box cool? Well, I guess you could just like ventilate the box, have some slits in it, you know. It doesn't really matter nowadays, but if any of you have the old transformer plugs at home, like the really big ones, yeah, the big ones, they'll have slits in it somewhere, I'm sure. They must do. There's no way for it to let the heat out. It's just a solid block.
I remember there's a block and there's like a plug.
This is for the computer.
Not the ones I picture. Maybe it's different safety standards. I don't know. Anyways, I would say as a way to keep the box cool, you could just put slits in it. Put vents in it. I don't know what the marking scheme says.
Changing flux linkage through aluminum casing due to magnetic field from transformer. That's 1 mark.
Was the question why does the transformer get hot or why does the box get hot?
No, it's just a reason for this heating effect and a way to reduce it. So yeah, technically it's why and how to do it. Why it happens and then how to reduce it.
What did it say for how to reduce it?
Remove casing.
No.
Yeah, it's a sensible method of reduction. For example, change material of casing or remove it, or reduce leakage of fuel from the core.
How do you stop the box from getting hot when you put the transformer in it? Simple. Just remove the box. Yeah, okay. I'm not so happy with that answer.
It says like changing flux linkage through aluminum casing due to magnetic field from transformer.
Maybe I'm mishearing the question. I'm picturing someone put the transformer in the aluminium box. Or are they saying that the transformer is made of aluminium?
It is kept inside the aluminum box.
It's definitely in an aluminium box. Okay. So what they're saying is one way you could help the heat is you could make the transformer run more efficiently. So usually we make the transformer, I think a good material to make the transformer from is iron. But I'm sure there's better materials that don't get as hot. Iron is a strong, cheap conductor that is good for the transformer. But perhaps there's some other material that would work even better for the transformer. Anyways, what's the next one?
B. A search coil is used to investigate magnetic fields. It consists of a circular coil of diameter 3 centimeters with 150 turns of wire.
Ah, okay. So you got a what's the radius or diameter?
3 centimeters.
3 centimeters, and you have this coil wrapped around it. Is it? How many times?
150.
150. Okay, go on.
V1. In a constant magnetic field, the maximum flux linkage experienced by the coil is 8.5 times 10 to minus 5 webers. This determines the magnetic field strength at this point.
That's, sorry, 8 webers.
Yeah.
That's the maximum flux you said.
Yeah.
That's the flux here. So they want the, what did they want?
They want the magnetic field strength.
The magnetic, the B.
Magnetic field strength, yeah.
So that's that over L. 8.5 times 10 to the minus 5 over 0.015 pi, 0.015 squared. So what's that now? Is that right? What did we get to that? What's that? 0.1202 Tesla. What's the answer in the market scheme on that?
2.12. Wait, no, sorry. 8.02 times 10 to minus 4.
8.
Yeah.
I might be mishearing the question. We'll get you to read it again to me. Can you read the question again?
In the constant magnetic field, the maximum flux linkage experienced by the coil is 8.5 to 10 minus 5 webers.
8.52.
No, 8.5.
There is 150 tons of wire.
Yeah, but the problem is they said that did they say the 8.5 is the maximum flux linkage?
They're using the equation BAN.
Well, the problem is by using the word flux linkage, they should have already included the 150 in that, you know. They didn't say maximum flux, they said the maximum flux linkage. And linkage means the total. So is it possible that they meant the maximum flux and then so we multiply the answer by 150? What is the right?
They went to about 150.
They did what?
Multiplied by 150.
Okay, so that is not the flux linkage. It's actually just the flux for one of them. I wish they didn't use the word linkage. Okay, so I need to multiply that by 150. 18 Tesla?
8.02.
Ah, hang on. 18? What's the answer in the marking scheme?
Yeah, 8.02 times.
No, but I'm getting 18. I'm getting 18 Tesla. I think I have to look at the question. I might have to. Yeah? Hang on, let me read it now.
Oh.
Hang on, let me get it. A search coil is used to investigate magnetic fields. It consists of a circular coil of diameter 3. So that's radius of 1.5 centimeters. And 150 turns. I assumed... I'm still not happy about the fact that they called it flux linkage. I might be missing something here. Matt, what did you figure out? Ah, no, you can't do that.
Nothing?
What were you thinking? Guys, I pictured it like this, but that could be wrong. There's no picture. It could have been like this. You have the coil, and you just have it wrapped around 150 times. I don't know. I'm not sure what the picture is. It doesn't matter because I'm not getting the right answer. Do you have the marking scheme?
Yes.
What did they do?
They times B by the area.
The Weber
Yeah.
is equals to B.
Yeah.
So
They divide 150.
yes, they did.
Ah, cool. I'm happy with that. Yeah. I'm happy. So, yes, that 150, they said flux linkage. That is the total. So before we started, we should have divided by 150. Yeah, so that it's divided by 150. Yeah, okay, no, I'm happy now. I'm happy. Yeah, 8 times 10 to the minus 4. So just so you know, the formula we're using is this, that the flux linkage is equal to NBA. Do you remember that formula? So they gave us the total, they gave us the N, they gave us the A, we just get the B. So we have to divide by 150.
Yes, the area of the coil.
Say again?
Is
Area of the coil, yeah. Yeah, so that's fine. It's that over NA. Yeah, okay. Right, what's next now? Who's reading this to me?
Eastern.
Yeah. What part are we on?
B2.
Okay.
The coil is rotated to an angle of 45 degrees to this magnetic field.
Ah. What is the B now?
Determine the flux linkage through the coil.
So it's just going to be times 1 over root 2? Yeah? What's the answer in the marking scheme, Andek? Is it 5.66?
6.01 times 10 to minus 5 times.
6?
6.05.
Did you say 45 degrees?
Yeah.
And they want, what do they want?
They want the flux linkage through the coil.
Oh, the flux linkage, sorry. So that's 8.5 divided by root 2. 6, you said? 6.01?
Yeah.
Yeah. Sorry. So it's the 8.5 times 10 to the minus 5 times 1 over root 2. Okay, next. Part 3, is it? Part 3, is it?
Yeah. The coil is now used to investigate a changing magnetic field. The maximum rate of change of the magnetic field through the coil is 2 millitesla per second.
The maximum rate of change of the...
magnetic field through the coil.
That's the B, okay. It's 2 millitesla per second.
Yeah.
Okay.
Assuming the coil is perpendicular to this field, determine the maximum EMF and use the circuit.
Okay, so that's the V equals minus N delta phi over delta T, which equals minus N delta BA over delta T. or equals, actually I should really put the n inside of it, minus delta NBA over T. Sorry, I'm getting a bit muddled up. I should take the B is the thing that's changing. The A is constant and the N is constant. So I'll take the A out. Okay, now, oh yeah, that's fine actually. I should have just done that. The N is, what's there, 150?
Yeah.
Yeah, so just putting in all the numbers. What's happening? Why isn't this working? 2.12 times 10 to the minus 4 volts?
Yeah.
Super. What's next?
Assuming all the other factors remain constant.
Oh, yeah, okay. Is this going to be if you change the blah?
No.
No, okay.
I take none of these.
Alright.
If the diameter of the search coil was increased by a factor of 3.
It is!
It is.
It is this. If the diameter was increased by a factor of 3
You use the effect of
of the voltage.
on the maximum EMF.
Yeah, okay. So, what happens if you increase the diameter by 3 is the question. What happens to the voltage, yeah? So look, area equals pi or squared. If you increase the diameter by 3, you make it 3 times bigger. It means you made the radius 3 times bigger. So if you make the radius 3 times bigger, what happens to the area? Is it 3 times bigger? It's 9 times bigger. Because if you go from 3r to 3r squared, that's 9 times bigger. Now how does that affect the voltage? Well, the area here will be 9 times bigger. So I'd imagine the answer is the voltage is also 9 times bigger.
Diameter is multiplied by 3 is to area 9.
Yeah. Okay, what's next, or is that it?
That's it for B3.
Okay. That's a good point to wrap it up then. We'll continue with 4 and 5 next time. When's our next class? Tomorrow?
Yes.
Okay, good. Good.
Probably.
Yeah.
Good.